I'm Leonardo Binni from Polytechnic University of Marche, Italy, and we're going to talk about here we go. We're talking about civil infrastructure. So we are talking about complex systems, and yeah, the management of such systems must adopt some basic principles. Those systems are usually dynamic systems and are based on multiple heterogeneous components. So, but they tend to show some regularities, and digital twins in civil infrastructures must have the aim of modeling such regularities when they show. And the contextualization of cross-domain and cross-scale information in the digital twin is required to develop knowledge about the system and to model those regularities. So from a knowledge engineering point of view, we are used to see this pyramid. We have to pass from data to information to knowledge. And yeah, there are some problems applying traditional data-driven and process-driven algorithms to the higher level of the pyramid to develop knowledge, because we have some risks, like to parallelize human-computer decision-making at the high level, because we are switching from we are not talking anymore about data, but about processes and behaviors at the higher level, and we have to take decision at the level. So it's risky to use non-explainable inferences like black box inferences. And for process-driven, we have some limited awareness given by the fact that those models are usually more vertical and in a single domain and not integrating multiple domains. And so they cannot handle uncertainty. And what we need at the high level of the pyramid is like a cognitive collaboration between humans and machines. So like Industry 5.0 claim. So we need some multi-domain features, some explainable inferences, and to handle uncertainty. And these are the features that are shown by knowledge-based models usually. So in this work, we aim to address the knowledge development challenge by using Bayesian networks in this, combining not data and process-driven, but data and knowledge-driven, capabilities. So Bayesian networks are probabilistic graphical models that can be used to build these kind of models based on expert elicitation or data training. So both capabilities, and they exhibit all the benefits of knowledge-based models. So explainable inferences, multi-domain variables, which is quite important, and can handle partial data, and among the others, of course. So it can also behave, as you can see, as a high level, I would call it orchestrator of the digital twin in a digital twin framework, where data coming from additional models could be fed in, or this model can fed additional process-driven or data-driven models with its output. So from a technological point of view, these processes, these models can be taught as microservices in a digital twin framework, and the process-driven, data-driven, maybe to the bottom of the pyramid, and then knowledge-driven at the top of the pyramid for the knowledge development to achieve the contextualization I was talking about. And so this has been formalized in our work using a digital twin platform we have built. I'm not gonna delve into it because it's another topic. If you want more information about it, we can catch up maybe later. And so just a little introduction. Is based on a microservice architecture, and we are integrating both agents, real and virtual agents all together, also along with heterogeneous data. So we have a whole integration of different data, static, dynamic data, whatever, in this kind of platform. And so what we did in this work, we basically integrate another microservice, which is a Bayesian network web service. It comes from Hugin.com. It's free. The commercial version has higher capabilities, but you can try it. And it is connected basically as a virtual sensor to the platform as a microservice, and we can query it. So feed it with some data, like from the sensor networks, from the bridge, for example, or we can, the other way, retrieve some data after the evidence has been input to the network. So we did a case study with the structural engineers from our department to demonstrate this digital twinning approach. Of course, we made some assumptions. This is not going to limit the approach, but it was needed for demonstration purposes, of course. And the objective was to build this diagnostic framework and with predictive capabilities on a bridge pier, a reinforced concrete bridge pier. And this pier is considered to be under different stress conditions, like bending behavior rather than the rocking behavior, so the full rigid rotation. And we did the model by eliciting the expert knowledge. So in this case, it's not data-driven, but we can apply data-driven capabilities later. First step of the analysis was to analyze the significant variables. So we took the Italian bridge guidelines in this work and chose the most significant variables for this the behavior of this pier. Some boundary conditions. We took some defectiveness, some static and dynamic input coming from accelerometers, for example, and inclinometers installed at the top of the pier. So the full list of variables we considered. We also had to do some discretization in order to simplify the example, of course. But and we modeled the network with two structural engineers based on this cause-effect relation, and also effect-cause relation. So it's both a diagnostic and deductive kind of modeling approach. And we basically elicited their knowledge throughout some brainstorming sessions, and we defined some concatenated probabilistic functions. So what's the probability that the top displacement of this measure will happen if the pier is bending with that inclination, something like that. And what we did basically was the modeling of the regularities we were talking about. So it's like understanding what could happen, okay? And this is the whole little network, integrating many different variables, static variables and dynamic variables. In this case, this is a basic scenario in which we have given no input to the network, so it's still working. So this is the handling partial data, so uncertainty handling capability. And we can see a statistical representation of all the possible behaviors that the peers can experience. And for example, in this case, of course, the peers is most probably in good conditions. And so this is the abductive inference direction rather than the deductive inference direction. We can give it input from one side or the other. So we started feeding the network with some input, not casual, but some design data and some dynamic input like the inclinometer measurement. So it is an I-pier with deep foundation, plastic hinge found at the base of the pier, and some medium level of inclination has been measured on top of the pier. We have some patterns, we have some regularities, like some behaviors become more likely to happen. The deflection, the bending behavior is more likely to happen rather than the rocking in this case at 98% probability. And so we have a medium risk level for top displacement. And in this case, a steel bearing will more likely fail. So we can verify this going on site, of course. And the abductive reasoning is that probably this is all caused by intense seismic action. So we are going to the top direction and see that earthquake level was higher at 53%. So just to go back to the cognitive collaboration, we went on site and measured the top displacement. Given that the model is explicit, we can access the model, access the inference and says, okay, it's not 20 millimeters, it's 5 millimeters top displacement. The model changes its inference and it's called counterfactual reasoning. And the output now, the regularity is that the bending behavior is actually confirmed, but the steel bearings are less likely to fail. So 70 from 60 percentile failure risk to 5%. So this is like the human-computer collaboration I was talking about at the high level of the pyramid. So thank you.